All right, algebra students, here we go. Notice that there are a lot more problems than we're used to seeing in the lesson practice. And also notice that this is really spread out because there's a lot of images. That's just how these kind of problems go. So we got a lot to do. Let's get going on it. The first thing we're going to do is make a scatter plot from the data in the table. What you need to do is simply take each one of these x points and y points that go together, the point 114, 227, 343, 453, 570, put them on an xy coordinate plane. When you're done, you're going to get a scatter plot that looks like this. Now, this one's actually going to have a line on it already. You won't have a line on it to start, but the first thing you need to do is graph all of your points. Hey, do these points look linear to you? Yes, they look like they're going in a straight line. This looks like it has a really strong correlation. Are these points perfectly linear? No. If they're real world data, they're really never going to be perfectly linear because of error. Okay, measurement error, and then just things that introduce themselves, and we're like I said, like friction, air resistance, things like that. I don't know what's being measured here, but these are not perfectly straight points that make a perfectly straight line, but they almost do, and that's good enough for a scatter plot. All right, so we made a scatter plot from the data table. The next thing I would do once I plotted all of these points is stick a straight edge on this graph. Now, here's one thing that's going to work for math problems. This does not work for real world data in science class. We're actually collecting data, but it works for math problems. What I'm going to do is I'm going to put a straight edge on these so I have the same number of points above and below. And I'm going to try my best to make the line that I'm going to draw pass through the origin of this graph, or at least pass through an exact point somewhere on the y axis. Hey, one more thing I'm going to point out by my y-axis, by the way. Do you notice it goes up to 85? Notice that this one counts up, so each line is by tens. Perfectly acceptable thing to do. Perfectly acceptable. You could count up by tens on the y-axis and then by ones on the x-axis, as long as you count up regularly on each axis, okay? I can't start counting by tens and then start counting by fives on the y-axis. That would be illegal. Same on the x-axis. I can't count up by ones and then start counting by twos. I need to be consistent on each axis. All right, so I've got my scatter plot. I've got my trend line now. The next thing I'm going to need to do is find an equation for the trend line. To do that, I just look at the line that's drawn, figure out what its y-intercept is. Okay, this one has a y-intercept of 0. Well, that makes it easy. And then I need to find the slope. Okay, so when I find the slope, what do I need to do? I'm going to look at the line and see if I can find a place where it passes through an exact intersection of the grid. This graph looks like it goes up about 70 and over 5 before it gets to the very first place where it crosses exactly at the intersection of two grid lines. That would be my guess. And why I'm looking for an intersection of grid lines is because from there I could figure out the slope. The slope I need because I need the equation, and I just calculate how far up it goes versus how far over it goes. Remember, how far up is it going there? 70. How far over? 5. However far up and over it goes between two places where it perfectly crosses the grid, like 0, 0 and 570, however far up and over it goes, that's going to be the slope. So the slope is going to be 70 over 5, or 14. 70 divided by 5 is 14. So I would say equation for the line that I just drew is very likely something like y equals 14x. Notice that my y-intercept is 0, so in my slope-intercept form here, here's the slope, 14, and it's plus 0. Now, the next one says I need to use a graphing calculator. Anytime you have a problem that tells you to use a graphing calculator, and you actually do have to use some kind of calculator, like calculating a line of best fit is the very first thing we've done that actually absolutely requires a calculator. You could use GeoGebra as your graphing calculator. I'm going to show you how to do this. So I'm going to go to GeoGebra, and we're going to check to see if I have an exact line of best fit with 14x. So I'm going to go ahead to start calculator, and now watch what I do. Instead of entering something directly over here on the left in the algebra section, like maybe you're used to, I'm going to go down here to table. And what I'm going to do is I'm going to enter all of my x values from the table. Notice this one counts up by 2's from 10. 10, 12, 14, 16, 18, 20. Let's do that. 10, 12, 14, 16. Oops. I can go back and change it. 18, 20. Okay. And then in my next column, I've got 25, 28, 30. 25, 28, 30. Okay. And then it's going to keep going. 35, 36, 40. 35, 36, 40. Now, notice this is a strong positive correlation, but it's not perfectly linear. But I'm still going to run a regression on it. It's going to ask me what kind of regression. Yeah, this is good. Hey, notice that this number down here, this is that number I was talking about, how strongly correlated that goes from -1 all the way up to 1. This is almost perfectly linear, almost perfectly correlated. The highest number it could possibly be down here is 1. All right, but I'm gonna plot this line, okay? And then we're gonna go back to algebra and look at my graph. 1.49 plus 10.05 is the line of best fit. And I think you saw before 1.49 plus 10.05. Mine just rounded a little bit more than that. All right, next, state whether there's a positive, a negative, or no correlation. Because this is a line with a negative slope, that is a negative correlation. Letter E, I need to state whether there's a positive, negative, or no correlation in this data. Well, look, as these numbers go up in X, okay, notice these numbers go up in the X row, the Y numbers go up as well. If both of them go up, that means that there's going to be a positive correlation. As one increases, the other increases. Now let's look at F, the outdoor temperature and the number of sweaters sold in a store. If the outdoor temperature goes down, the number of sweaters sold is going to go up. One goes down, one goes up. That's negative correlation. And then finally, hair color and length. Do people with different colored hair automatically, because of their hair color, have longer or shorter hair? That's going to be no correlation. There it is. Because they're not related to each other. All right, match each situation with the letter model, the number of the model that it best represents. The scatter plot down here. Time spent exercising and calories burned. You spend more time exercising, you burn more calories. Both of them are going to go up together. This one's going to be graph 2. There it is. The number of dishes washed and the number of ounces of detergent left in the bottle. As you wash more dishes, the amount of detergent is going to go down. Those are going to be negatively correlated. That's graph 1. And then lastly, the population of a country and the number of states in the country. Um, the population of a country and the number of states wouldn't necessarily be correlated to each other, because you can break up the country into any number of states that you want. You can make the argument maybe that it might be correlated one way or the other, but this one's actually going to be no correlation, because it really doesn't have to be a relationship between the population of a country and the number of states. You can make as many states as you want for a country, regardless of how many people live there. All right. Next, the table shows the number of people employed in agriculture in the United States from the year 1940 to the year 2000. That's this. Draw a scatter plot and trend line for the data. Again, I have this one pre-done as the book did it. So all we would do is we plot the bottom line as, the top line as X and the bottom line as Y. And we would make each of these an XY coordinate pair. So it's going to look something like this. X, Y, X, Y. Okay. Next, we're going to use the trend line to make a prediction for the population in the year 2010. So what we need to do, the best thing for us to do first is to actually find an equation for this. We could, okay, so actually here, for this trend line, we're going to use a straight edge to draw our trend line on the data. We're going to make sure there's just as much data above the trend line as there is below. And we're going to try to make it so the data is just as far above as below the trend line. So that's what this trend line is. For 2010 is going to be right here. We're going to figure out about what the point is going to be at 2010. So this is a population in millions. We're not quite going to be at 2 million. We're going to be way over 1 million. So like maybe 1.8 million. Let's see what we got here. 1.5 million. Okay, I could buy that. 2010, let's see, this is counting up by tens. At 2010, we might be at 1.5 million. 1.8 million would be a good answer as well. Find the equation for a line of best fit using a graphing calculator. It says to the nearest thousandth. I can do that in GeoGebra. Yeah, let's do it. Okay, so what I'm going to do is I'm just going to plot my years. Notice it starts at 9. Let's see. Actually, we're going to go and we're just going to purge all of our current data. We start at 1940 and we count up by 10. 1940, 1950, 1960, 1970, 1980, 1990, and I think we stop at 2000. Is that right, or do we go to 2010? 2000. 9.5, 7.2, 5.5, 9.5, 7.2, 5.5, and then we're going to keep going. 3.5, 3.4, 3.2, 3.5, 3.4, 3.2, and then lastly we got 2.5. Okay. Now, I am zoomed way too far in on this graph to actually see it. So let me just see if I can pinch zoom way out. There's all of our data. Now I'm going to zoom way in on the data. Does this look like it could be potentially linear? Yeah, it's a pretty good linear fit. It's not perfect like all of these, but we could make a linear fit for it. So what I'm going to do is I'm going to draw my regression line. We're going to plot it. Let's see. And then to make enough, um, so notice where I went to settings and then I clicked on the gear again to go to settings. I need to change this to 3 decimal places to get to the thousandths place. I'm going to save those settings. So again, I click the little gear icon, then I click the gear icon again, and then I get to round it to 3 decimal places. All right, let's go back out to the Algebra tab and look at our equation. Negative 0.111x. So our slope is negative 0.111, and it's plus a y-intercept of 223.782. Let's just see if we got the same thing that the book got for that equation here. Let's see if I can find that equation here. There it is. Okay. Yep, there it is. And then use the equation for the line of best fit to estimate the population year 2010. So what I'm going to do is I'm going to plug in 2010 for x. It's going to be negative 0.111 times 2010 plus, and then let's see, it was plus 223.782. And my answer is 0.672 million. Let's just see what the answer would have been. 0.5 million. So remember, we used our trend line up here to make a prediction of 1.5 million. Remember, I guessed 1.8 million from the trend line, not zero point 0.8, but 1.8. The actual equation yields an actual best fit number of 0.5 million. So we were quite a ways off. But that's kind of what happens with trend lines. It is way better to use a calculator than it is for you to just draw it in yourself. All right, that is how you make trend lines, lines of scatter plots, trend lines, and then lines of best fit using a calculator. You're ready to do the assignment for next time.